So today we're going to kind of set the context a little bit more. We want to talk about the next step and potential future technologies that start from the blockchain space. Blockchain needs hydrogen infrastructure to utilize. Let's just state that so Bitcoin is the first experiment in kind of decentralized applications. And Ethereum, which you probably all know, is the generalized blockchain which implements security programming language. And very early on in the finance of Ethereum, thought about the possibilities of how the internet can be served by this new technology. And they realized that all this research into peer-to-peer technologies may come to fruition. We supply the last missing bit of the puzzle, incentivization. And this is going to be the major thread in today's talk. And first, I would like to give it over to Aron, who will introduce the swarm incentivization scheme.
Thank you. So I'm going to talk about Swarm, which is often called the content storage layer for Ethereum, but it is a lot more, and we want to present today all of this delivery network, storage network could allow us to do in the so-called Web 3.0. I want to talk about specifically what new things we can do now that we have this blockchain Ethereum integration, because we've already had peer-to-peer data stuff, we've got BitTorrent for a while, but the fact that we can integrate with Ethereum just means that we've got a whole different, the dynamics are completely different because of the way we can fine-tune and program everyone's incentives. So that's what I'm presenting. Let me start with content delivery. Swarm is a content delivery network, if you look at it from a certain angle. So let me start with how would you get data out of a swarm of nodes all storing a little bit of data. Within the swarm, everything has an ID. You have an ID, and every bit of data has an ID. And the ID is its address. So if you have a list of swarm nodes connected in a network, they all have an address. We know which ones are close together, which ones are far apart. That's you, one of the nodes in the network. And then you want to get a document or some data in the swarm, and you would have to look up that piece of data's ID address. So if its address is H, that has a location in the address space, and we'd have to retrieve the data from that address. So what does that mean? Retrieve it from that address. It means we will look at those nodes, those peer-to-peer nodes whose own address is closest to the address of the data, and that's where the data is going to be stored. So, how does that work? This is us, we're trying to retrieve data. That's the address of the data. That's the closest node to the data, and it's going to store little data packet there, drawn in orange. Instead of connecting to that peer, you don't want to always launch new connections for every bit of data. You have your peers that you're connected to, close by. The way that the routing works in Swarm, of all your peers, you always have one, at least, whose address is closer to a given piece of data than you are. You just ask that peer, could you find this data for me? With a request, that peer will pass it forward, it will be passed forward, and it will make its way in the swarm until it reaches the closest node. And from there, the data can be returned all the way back to the retriever. So it's a very peer-to-peer system. So that's great. These nodes along the way helped us, but why would they do that? Well, they would do that because we incentivize them to play nice. And backing this up is the Swarm Accounting Protocol. The Swarm Accounting Protocol keeps track of all the bandwidth provided by the peers and tries to account for that. Bandwidth accounting in this network system isn't absolute. It's not all bandwidth I have, but for every peer, I have to keep track of the bandwidth used. It's the only thing that makes sense in the peer-to-peer context. So here's me. Here's a peer. I provide some data, they provide some data. The only meaningful measure is the difference between the data delivered and the data received. And whenever that goes out of balance, a payment has to be made to rebalance that. I mean, if I get data from you and supply data from you, you never need to make a payment, perhaps. But when it's in balance, we do. Now, it's impossible to pay for every piece of data. That would just be way too many transactions. It's completely prohibitive. So we could think about doing it in batch. Just every, I don't know, 50 megabytes or whatever units of measure you have. But even that would be an unacceptable level of blockchain code. We really want to keep these transactions off the chain as much as possible. So what Swarm does, it uses a smart contract on Ethereum, which works like a checkbook. I launch a checkbook, I deposit Ether, and then from that moment on, I can write checks to you. And these checks you can hold on to, and if you don't trust me, you can immediately send them to the Ethereum blockchain and claim your share of money that I owe you, or you can just wait collecting checks, and the clever thing is, they're cumulative, so only ever the very last check that I gave you, you need to send it to the blockchain. So this way you can really reduce the number of transactions needed. You can keep it all off-chain. And if this sounds to you like payment channels, it's similar. It's not quite a payment channel, although Swap will soon also be working with payment channels. Payment channel system Raiden. I don't know if you're familiar, it's essentially what Lightning Network is to Bitcoin, Raiden is to Ethereum, and we're working with them for integration. Difference, very quickly only, the difference between the checkbook and the channel version, they're both good for moving transactions off-chain. The checkbook's benefit is that this is a very low barrier to entry. If I have a checkbook contract launched, I can start paying each and every one of you. But if we are in a payment channel network, it would only work if you all individually join the network somehow. On the other hand, a check can bounce, but payment channels are safe. So it depends on context. But no matter how we're actually going to implement it, the key is that this data distribution network, by the fact that we have integrated with Ethereum, allows us to program the incentives of every single node along the way, and thereby control the behavior of a huge cluster of nodes. One example I just want to give, like an emergent property, is that popular content is automatically distributed and cached. So that as a content delivery network, this rule alone means that this network is auto-scaling. So remember our retrieval. We're up there in the corner and we have all these nodes and we send retrieval requests to get that data, and the data made it back to us. Now the nodes along the way, they didn't really care for the data. They've still got it, as you can see, they've cached it, but maybe some of them will delete it, and it disappears. That's fine, they're allowed to do that, but they have an interest in not doing that. In particular, this node down here, which is still relatively close to the data, has an interest to keep it, because if there's a new request by someone else and they send forward their request somewhere and their requests hit a node that has a cache, that node can return the data and make a profit. So popular content will be automatically cached and distributed. We don't even have to make that as a rule. It's just profit maximizing nodes will automatically cache it. So that's really great for popular content. Unpopular content, private content, that's a whole other matter. That's now a question not of delivery, but of storage. Like, I want to back up an encrypted copy of my passport and birth certificate. I want it to be there in 2 years' time, but nobody's going to access it. So nobody's going to make profit delivering it. So we need a different method. So how do we pay for storage? How do we incentivize nodes to store? Well, it sounds dumb. The easiest way is pay nodes to store your content. Right? That's the basic idea. Just the question is, how do you pay? If I pay you up front and then you delete my data, then I'm screwed. If I say I'll pay you in a year from now and you store it, and then a year from now I don't pay you, then you're screwed. So we have to come up with some kind of a balanced way. But paying, the first part is pay as you go. Pay as you store, it's called that. The idea is, I want something stored. I will put up a deposit in a smart contract, and the way it works, every so often, maybe once a month or whatever our time frame is, I can issue a proof of custody request. And then when you return a valid proof of custody to prove that you still have the data, that unlocks the next payment. And the nice thing, the way the smart contract works is, when I have put up the initial deposit, I no longer have control of that money. You will get that if you store my data. I've already committed to it. But in order to unlock it, you actually have to prove continually that you're storing my data. And this is much better than just data retrieval because a proof of custody is a really small bit of data. It's a single hash. And that can you know, it can give you, depending on how you set it up, security over huge, you know, data collections. Yeah, this is a conditional escrow condition. This deferred payment, they pay up front and unlock with proof of custody. And the fact that we're on Ethereum means that the logic can be encoded in a smart contract, and that smart contract could be a judge contract for an off-chain payment channel. So this entire storage logic can be moved off the chain, just by the mere fact that we can have the judge on-chain, that if there is a dispute, you can ask the judge. But as we always say, if the judge is deterministic, you never need to ask it for its opinion. So this can all be done off-chain as well. Yeah, that's great. That's what we call the positive incentivization side. We're paying you to store the data. But if you then still delete my passport and birth certificate, you're out of profit, but I'm still kind of pissed off because you agreed to store my data. So we wanted something else, a second component, a sort of negative, punitive incentivization, that if you don't agree, if you don't you know, store the data when you promised, you will actually be punished and lose data. And that is, and that leads us to the swear contract. If you swear to store my data, you invoke this contract. So how does that work? The swear contract is one that takes your deposits. You have to put up a huge security deposit if you want to be a storing node. Then you're registered. Once you're registered, you can sell storage promises on the storage market. And so it's actually very simple to add on this to the ordinary swarm. Now I've written here, the implementation is swarm plus receipts, but that doesn't mean anything. I showed you the picture. The ordinary way that we distribute data in the swarm. Now I said at the beginning, data is always stored near its address. But what does that mean? How does it even get there? Well, any data entering the swarm from the owner to making its way towards its address, trying to be stored at the address, or at least node closest to the address. I will, in a process called syncing, to the peers that are closer to the address space, they will pass it on, and so on. The data sort of makes its own way to its storage location. And this is a content-addressed storage network, so the content finds its way to its address. So that's great. And if we're now looking for the storage with promises, the sworn storage network, it works exactly the same way, except that the registered nodes along the way always have to issue a receipt saying that they received the data, and this receipt acts as a promise that they will actually keep it, that will stay with registered nodes. So it's essentially the same diagram. Store requests are just receipted sync requests. It's very, the implementation there is relatively straightforward. Yeah, the last part is the swindle contract. It is what happens when you lose my data. Well, if you lose my data, the short end of it is you lose your deposit. Right? That's what's supposed to be. That's why it's a security deposit. And the mechanism is such: if I want to retrieve data, it's not there, but I have the receipt. I sue you at the blockchain, and if you're a storing node, either you defend yourself by saying, "Hey, I have the data. Here it is," or you say, "I gave it on to that guy. Here's the next receipt," along that chain that I had in the previous diagram. But that process will end at some point with a node that either has the data or loses the deposit. So this litigation feature is you always need to have that. But this is sort of you always have these three parts: accounting with security deposits and a judge in terms of disputes. And this format is actually applicable to very different use cases than just the storage that I mentioned now. But seeing as we're short on time, I will now give to Viktor, who will start off talking about a bit more about the underlying, how is data represented in the swarm, and then what we can build on top of that. So,
thanks. Sorry guys, if you don't mind, let's take city. Yeah. So in generic, since this pattern is a generic way to create incentive systems and secure operation of health, we kind of playfully call it swap, swear, and swindle. So let's move on to the next problem. So far we talked about these pieces of data completely, not specified what we actually need. So in fact, under the hood, when we talk about this data that we actually litigate and insure, we talk about chunks. What are chunks? So every kind of file, document, and data that we upload to the swarm is chopped up into like fixed size pieces, chunks, and they are like arbitrarily set as 4 kilobytes. And once you set the data level that you see on the bottom chunks, you hash them, and the hash is basically the hash is the address that you associate with the node. This is called content addressing, which means that the address is deterministically derived from what the data is. This is very, very important for data. And once you have these hashes, which are 32 bytes each, if you have 128 of them, then you can package them up into the next level of chunk. Because that exactly gives you 4 kilobytes. Now if you have that, and you continue this process, you basically build up a Merkle tree representation of the file. Now from this Merkle tree, the most important bit is that it's completely integrity protected. You can even do random access, which means that you can reach only like part of the file and know that it's perfectly legit and without downloading the entire file. So that means that, for example, you can skip in a movie and to stream. Since this, the way you access a particular segment of a file is through the top root node, and you go through all these hashed chunks, it's basically equivalent to the Merkle proof of that segment, which is very important because that's exactly what used for proof of custody schemes most of the time. We don't go into that exact detail. In the orange paper that we published, we go into detail about how we extend the proof of custody scheme for really big document collections in an efficient way. Now, notice also that if you think of this traversal from the root to a segment of a data as like going through these intermediate branching nodes, and actually if you traverse it and find a segment, you can on the way note which index of the branching node you have to take. So it's which branch you have to take. And since it's 128, you can think of it as the ASCII character set. So that's just basically an idea to give you that you can represent each segment of a big file by a sequence of ASCII characters. The length of this is basically the logarithm of the length of the file. Because that's how many levels you have to traverse. Why is this interesting? This looks like a very arcane fact. Well, it's interesting because you can immediately see that these Merkle structures can be thought of as indexes, iterable indexes over pieces of data. Now, what if we generalize this idea? That's exactly what the swarm manifest is. So manifests are basically Merkle trees, but they're generalized. It's not a chunk tree in that it's not balanced. You can imagine any string or any key space item to match to a swarm hash. What does that mean? It means that you can index swarm assets to any kind of digital file, let's say a document. You can index them to a particular string. What does that mean? Well, it means that you can immediately use that as a URL scheme, URL indexing. How does it work? So let's see an example. So for example, when you see this address, this is the swarm landing page. This looks like this. As you see, it's just a single static HTML page. When swarm retrieves that, what happens actually under the hood is that it retrieves this manifest file. This manifest file, as I said, is just an index of certain strings to hashes, which a hash represents the entire document. And this is serialized in the JSON format. It looks like maybe unintelligible for some of you. And it's, for example, when you see the first bit, for example, the swarm files, that path, or the partial path, maps to a hash. That's one manifest entry, so to say. you can think of it as a partial path that attaches to a file. Well, actually, in that case, this file is not a file, but actually another manifest, which represents the subpath, continuing from small files. So this basically is a routing table from say a domain. It can be conceived of that. And the other way you can look at it is, for example, you can also think of it as a directory tree. So let's look at that way. So for example, if the same Swarm landing page is viewed through a tab called File Manager, then it looks like this. So as you can see, it exactly represents this path as if they were directories. And the special thing is that all the slashes are handled. These different slashes are considered as directory separators. Well, why is this so interesting? Well, it's interesting because if there's a two-way translation between how the data is represented and indexed in Swarm, although they are distributed in little chunks all over, like millions of nodes, if you can directly map that to a directory tree representation, then you can have a translation between file systems and the Swarm representation of a virtual server, basically. So that allows for us to have to basically allow us to write a file system driver that has Swarm as a backend that would allow things like you could buy a computer, like buy a laptop with a very minimal Swarm client, you open it up, and you just pick your favorite operating system, and it will immediately download the whole OS or operating system in an on-demand way. You could put in your home directory, which you also uploaded as backup and insured on the blockchain. So you could have access to a computer with any operating system, right? Or it's an interesting. This is of course far in the future. But more immediate use cases, like you can have a simple file system API, which means that you can say that I want to upload a directory to Swarm, and it can preserve all these paths. Or you can have a Dropbox feature that can sync between a Swarm virtual node and your file system directory. So far we talked about how this path can actually, given a root node, how path can, like a human readable path potentially, can index a particular document. Now, if you take it one step further and say that the root hash of the main document version manifest can also be registered on the blockchain with a human readable name, then you have the entire way the internet is organized now. So you can have basically domain names, registration, and you can have the URL path, which can lead to new assets. This is a very powerful system. Even though, so it can basically mimic a server that has like a sitemap of a server without all the data ever having to be in one place. It's distributed among thousands of nodes in little chunks. Now, so when you do the browsing in such a system, you can benefit from associating extra data to this particular path. So, for example, the path that's for example the orange paper. You can say that, oh, actually this is intellectual property. You can only read it if you pay this and this royalty. So you can have like payment triggers. You have copyright information, all kinds of access control if you want. I mean, obviously these are better viewed as opt-in systems on this. This is kind of just a detail. Okay, so. Okay, so far we talked about how static content is served. But obviously, if you're really serious to want Swarm to serve as the base layer for the internet, you really have to cater for real-time interactive web applications. What are the needs for these web applications? Well, they most often like to offer some sort of communication services. So you have like chats, you have all the multimedia channeling, you have real-time data feeds, you have your news feed. So basically, these are the ways in which even static client-side JavaScript pages provide you with personalized content. They basically suck data in from your friends, from any kind of data source. These days, usually these are databases and APIs that are used. So what's the equivalent of this on the blockchain? So how does, first of all, let's ask the question, how does dynamic content move around? Well, the answer is that we can use the same routing and incentive system as we used for storage and retrieval. It's actually, what kind of communication and interactions are we used to? Well, we have all these different medium like tweets, Facebook status updates, we watch TV, we video conferences, they do phone calls. What are these? These most of it are provided by some sort of private entities and companies, and they are really separate from each other and siloed away. And some of the commonalities between these are not really captured. Some of the limitations are quite arbitrary. For example, I don't know how many of you ever wanted to like or dislike a chat room contribution. You can't do that. You can only do that with the Facebook at one. So why are these services provided by private entities? And after all, we can just say that these are all just pushing and pulling different types of data between particular nodes, and maybe involves a bit of storage if they are not expiring. So we can basically use the same infrastructure as for retrieval and storage, and just use a certain taxonomy to classify all these different communication modalities. And here are a few examples of what questions you could ask. For example, is it addressed to specific recipients or not? If you deliver something, if they are not at home, so to say, is it re-delivered? Or, for example, is it actually stored ever on the content address? For example, in a case of an email or attachment, this would be typically the case. Or is it completely ephemeral, like a non-recorded phone call? That you have like a session where data comes and everybody forgets. So these various dimensions of classification are simply parameterizations of the messaging protocol. If you can think of it as so the vision is that all these different use cases can be implemented by the same underlying service, and obviously what benefits can it come with. We can already use the incentivized message relay that we used with the swap protocol. We can use the deterministic routing for message delivery, which is probably much more efficient than the alternative Whisper. I don't know if you, I didn't mention this, but Whisper, Swarm, and Ethereum is supposed to be the holy trinity of Web3 according to the original visionaries. And we already have like priority queues that are also used for syncing. And we can use the insured storage to, for example, make sure that, okay, I'm sending you an email, but hey, all these nodes, if you can't deliver to the person, please hold on to it because it's insured, and it has an expiry. And that can make sure that the person stores it. It's like basically you have a decentralized mailbox service. So when you come online, you just download it from them. Okay, so next, I wanted to, so basically this project is called PS, because the protocol name for Swarm is PS, which is the name of the Swarm, and this is Whisper, because it's mixed in with the Whisper protocol anyway. It's just a gimmick. This is how I entertain myself also. So I think I will skip this part. So basically, I wanted to talk about how peer-to-peer technologies also can cope with a really serious problem of multimedia content dissemination, namely that all these media server solutions are facing the problem of scalability, because especially in the case of low latency streaming, basically one-to-many broadcast situations when it's live. Because in those cases, the server load cannot do it. So there's all kinds of solutions to that, like WebArtist is trying to solve basically all these problems with not having a peer-to-peer system proper on and the real internet at the moment. So we believe that, that by combining the peer-to-peer routing and in some clever way with incentivization, we can have a very robust solution for basically for this multi-bit rate and low latency streaming. And interestingly, I mean, this is you have to realize that this is a bit of a dream phase thing. So this talk is a little bit of visionary, and not much of it is implemented. But as far as I can see, if this solution we can pull off, then it seems to me that the same algorithm can be used for basically video conferencing, because peer-to-peer relations are interchangeable. So you can be a server as well as a client. So that if one-to-many broadcast works, then it works as the same way the other way around, and therefore it can support really good quality, low latency streaming. If you want, we can return to this in the questions, but I would like to skip it. So we call this the Swatch project streaming. Well, it says steaming, but it's supposed to be streaming with adaptive transmission channels. Okay, so third. So what is this? So we talked about how information moves around, maybe a bit of like special way of transferring session data in the multicast case. But what is it actually that is the source of this data that's put in this dynamic content context? Well, it's usually in the usual web stack. Everybody knows the LAMP stack of the old web development. In the LAMP stack, the M stands for MySQL. So it's in the backend, all kinds of user data and like the business logic is in databases. This proved to be a very robust solution because, like, let's see what alternatives there is in the blockchain space. So you can obviously program the blockchain in the blockchain contracts all the business logic that your application has, and that certainly is a possibility, but the problem is that to put every Facebook like on the blockchain is very unlikely to be scalable. You really can't afford it. It's really very expensive to have millions of computers calculating transactions. And it's obviously too slow, so for some applications you really need a resolution that is higher than what the block time allows, even though in the case of Ethereum it's 15 seconds and not 10 minutes like in the case of Bitcoin. Even that might be too slow for some applications. So you can also choose like the local storage for the private data, but that's limited to the scope, like what the user wants to use. There is kind of shared data which everybody wants to access. In that case, you need some sort of centralized database, or not. And our solution is that you can actually have a completely distributed database over Swarm, and that can at the same time satisfy, like basically have the best of both worlds. So it can have the advantage that it's cheap. It's similar to private local storage, but at the same time verifiable, which is the advantage of stuff that's on the blockchain. So how is it done? The idea is that it provides a structure based on the manifest. So remember that I talked about all this indexing, that the manifest can basically map any string to an arbitrary data object. So what is it? This is basically a key value store, right? You can associate any key with a record, and if that record has a conventional structure, then obviously new index from a major database table that like lists, I don't know, node IDs to subscription records, for example. It can be indexed in a different way. So for example, it can be re-indexed based on what you subscribe to, and it's an automatic process. So it allows for re-indexing, and with all these conventions of data and how tables are organized, one can basically define certain ways of re-indexing and certain ways of navigate through the swarm to find answers to particular database queries. Now, obviously, database queries are, involve much heavier computation potentially, and that's why it's never going to be really scalable to we talked about security. So yes, security is provided by the fact that the manifests have a Merkle property. So every insertion in the swarm database can actually be challenged and verified on the blockchain for real. So that means that with the swap, swear, and swindle pattern, you can basically guarantee that off-chain database handling is according to some rules. Okay, so let's go to scalability, because that's exactly the problem. So it's all beautiful and it's verifiable and cheap, but it's ridiculous. I mean, I have to go through like 1,000 requests on like network connections to have an answer to like, a simple query. This is just not on a scale, obviously. So what do we use? Well, we use established database technology. I mean, we're not going to throw it away, but with the extra twist that you have these reference data structures on the swarm, which everybody can walk through, verify, challenge any node's behavior on the blockchain. And what's the scalable distribution? Well, to have basically a computational market. You have specialized nodes which commit to, say, whenever I see someone's subscription to that site, I re-index that table according to what's subscribed. So I provide you with another, table which retrieves. If you ask me who I send notifications about updates to this site, I will give you the names. So it's like the reverse indexing for that context. And in the same way, like all kinds of updates or derivative data, like full text search indexes and aggregate statistics, can also be computationally proved. And anyone who's misbehaving and miscalculates it can be made accountable on the blockchain with automated processes and basically total security. And query caching and so retrieval acceleration by caching queries and using proper good query database solutions are solutions for maybe scalable and maybe proper in the context of like real-time interactive web apps. So for example, one example for this is for example BigChain, for example, building company. That's a very good solution for that. If you want the questions, I can go into details about this. So the fourth property is sustainability, which obviously relates to our main theme and thread, which is the swap, swear, and swindle pattern. I already touched upon this, that even the verifiability and putting up a deposit and basically make sure that the database access, query, and insertion and everything works according to particular rules. This all sounds very nice. So I don't know if we have time to go through the example, probably not. So I just skip to the real ultimate conclusion where we come to full circle. So how about we put the actual Ethereum state on the swarm in this form of the database? That's going to be like the vicious circle, and it's possible. And what is this project is called Sword, it doesn't matter. And what it basically arrives at is a bit like the simple payment verification. They call it in the Bitcoin space. We call it the light client or light Ethereum state, less protocol. It's basically a similar technique to that, which similar to the empty computer that you open and download the operating system in an internet protected way. It's similar. You can just immediately sync to the most current state of the Ethereum state network, and later use that you can, if you trust the system currently, then you can obviously immediately start transactions with the blockchain. But if you don't, you can later simply go back in and verify part of the state or verify the entire state from day one, from the Genesis block. And so that provides on-demand data retrieval based on Swarm, which means that you can have a flexible transition from being a live client to a full archival node. And it's also solves the scalability problem related to the fact that the blockchain state is pretty big actually. It's already like gigabytes big, and we're very early on in this project. And of course this can be solved with like checkpointing and all kinds of solutions, but ultimately this sharing of the data on Swarm is quite a great idea. And of course if we have if we top it up with the possibility of having decentralized ways to solve more complex queries over this simple database, then we basically arrive at a decentralized model of blockchain explorers. So like certain queries, for example, what transactions came to this particular account between these dates, these are not like directly supported by the Ethereum clients because they don't index it that way. But if you use the Swarm and like these decentralized technologies, you can have completely decentralized blockchain explorer API available. And sorry. So in my dream world, this is kind of the just a partial representation of what I think the ecosystem might look like. So in the middle, that's like the trinity of Ethereum, Swarm, and Whisper, and around that, like all these kind of technologies that we think Web3 proper decentralized applications will ultimately use. I mean, some of these are a bit contrived, some of them are more low level than others, but it's just a kind of good depiction what we can think of. What you see in the middle down, that's the logo of the Mist browser, which is supposed to be the key component to bring a bit wider adoption for Ethereum. I mean, I think it depends on having good applications that are useful to people, not really the interface. Anyway, so where are we with all this? Because this is a beautiful dream that I presented to you, and this is obviously, I don't know, 10 years of work for 20 people. If I really follow up a lot of my ideas. But at the moment, so the Ethereum client development is at the homestead milestone. Next milestone is called Metropolis, which is marked by the release of the Mist browser, hopefully with full Swarm integration. And so more specifically about Swarm, because that's kind of more my project or our project. The status is that it has the Go and the Go implementation as the reference client. We are doing a series of proof of concept developments. We are iteration 2, and the code has just been merged to the Go Ethereum client's develop branch, which means that it's integrated with the get client. But at the moment, it's not in any way default switched on, and really not recommended to use it on the mainnet, especially for the payment stuff. And so, thanks to Microsoft's sponsorship, the Azure Cloud is hosting a testnet of 100 plus nodes, which you, in a week's time, when we release this, the demonized version of Swarm, you'll be encouraged to join this network and help us debug the stuff. And this is kind of very early stages of this development. So, how it can be used? As I said, it's used. Swarm is used in a daemon form, which means that you can communicate with any Ethereum client. There's APIs, there's JSON RPC, HTTP proxy, and bindings for JavaScript and command line. Let's not go into that. And finally, I would like to conclude with an encouragement. If you guys are interested, please join our channels, the Swarm channel on Twitter, and you can join our research group. There's a reading group and reading seminar every week, and it's kind of the basis for the Orange Papers series that we're writing. And below that you can find the names that I would like to thank the contribution of. These are the people who are instrumental and very important in developing Swarm. And with that, I would like to conclude. Thank you very much.